All right. So we're doing mixtures of acids. Now, mixtures of acids obviously could be like two weak acids, or they could be two strong acids, or they could be a strong or weak acid. And one of the problems that you had the other night was mixing two strong acids. And so if you have two strong acids, because it's a 100% dissociation, you're going to add those two concentrations. So if I have So if I have, for example, and I'm kind of like winging this because I don't even have an example of this, so I'm really just throwing this out here. 0.010 molar HCl and 0.100 molar HNO3, and I'm mixing them together. So from this one, the concentration of H plus is going to be equal to 0.010. And then from this one, the concentration of H plus is going to be 0.100. So therefore, the concentration of H plus is going to be equal to 0.100 plus 0.010, which is equal to okay? Now, the reason is because 100% dissociation. So we know that the concentration of the hydrogen is going to be the same as the original concentration of the acid. I mean, the other way to look at it, which is kind of the way that I looked at it, was, oh, so it's this strong acid plus this strong acid. It doesn't matter what the strong acid is, they're both going to dissociate 100%. So I might as well just be adding this and another one of the hydrochloric acid. They're both going to dissociate at 100%. Okay? So the second possibility would be a strong acid and a weak acid. So for example, 0.10 molar HCl and 0.10 molar formic acid. And this one has a Ka of 1.8 times 10 to the minus 4. And minus 4 is really the line where it starts to go into this is kind of a weak acid. So also involved with this would be water, which has a Kw of 1.0 times 10 to the minus 14, which is negligible. We have to kind of keep it in mind because there are H pluses coming from the water, so you always have to keep in mind that the water is there, because in some cases the water might be important, not so much in this case. So what happens here is that, and it's kind of interesting, the hydrogen in the hydrochloric acid actually sort of suppresses the hydrogen coming out of the weak acid. So let's take a look at this. So we know that the hydrogen from the hydrochloric acid is equal to 0.10 because it's got 100% dissociation. So we know that, right? And so what we really want to do is we want to add the H plus to the from the formic acid, right? So we're going to have to do an ice on that, right? So real quick ice. Oh, sorry, no 2. I don't know what I'm doing there. Is there an H in the formic acid? No. O2. There you go. All right. So this one is super easy, right? 1, 0, and then minus x and 0.010 minus x. But the hydrogen already has a concentration. From the HCl, it has a concentration of 0.10. And then it's going to get more from the formic acid. So ultimately, its concentration is going to be 0.1 plus x. And then the ion is going to be at 0. And then it's going to add x. And then ultimately, it's going to be just x, right?
So is the H plus from HCl
Because
because it's a strong acid?
it's a strong acid. So 100% of it is shifting over, so it's already got that combined with it, right? So now my Ka is 1.8 times 10 to the minus 4. And I have 0.10 plus x times x over 0.10 minus x. Now I'm going to assume my 5%. And when I do that, I can cancel this one. And I can cancel this one. Now, I can't cancel the multiplication one because when we multiply, it makes a big difference. It doesn't make such a big difference when we add. And the idea of the 5% is that statistically adding it is insignificant because it is so small that when you add it, significant figure-wise, it will not show up. That's why, right? But when you multiply it, it is going to make a difference because you're going to add those exponents, right? Does that make sense? But when you add it, it's so small, it's not going to show up. All right? Okay. So now I'm going to solve for x. So you solve for x, and still it's pretty easy to solve because there's no, there's no x squared. So you end up with x is equal to 1.8 times 10 to the minus 4 because the x's cancel. I mean, the 0.1's cancel, right? So now I do my my 5%, 1.8 times 10 to the minus 4 divided by 0.10, and it works. I don't even have to go any farther. That's definitely going to be good. All right. And so now I know that my concentration of H plus is equal to 0.10 plus 1.8 times 10 to the minus 4. Well, that's just not even significantly relative at all. So 0.10. So in other words, So this is the HCl, right, from the HCl, and this is from the formic acid. It's just not even statistically significant because the hydrochloric acid is so strong that what comes from the formic acid just is not even relevant, right? So we don't even have to count it. So what's the point of this? The point of this is that when you're mixing a strong acid, if the volumes are similar, right? If the volumes are similar, or strong acid is greater, the weak acid, the H plus from the weak acid is irrelevant. Okay? Yeah, sorry. All right, it just doesn't matter. So basically, you're going to get, that's what's going to happen, is for the most part, you're going to get, these will be multiple choice questions, right? And again, if you know from that list that it's a strong acid and a weak acid, it's an instant, an instant answer. Okay? All right, let's take a look at the third option of mixing acids. 2 weak acids. So we still have the same 3 sources as before. Those 3 sources are the 2 acids plus water. Those are the sources, all right? So the Kas have to differ. And then the stronger of the 2, which is the higher Ka, right? Will contribute the most H plus. And so for the most part, you're going to take the concentration of the stronger one. Now, you got to think about the relevance of the Kas. I mean, if they're very similar, which chances are they aren't, then you're going to have to, if the concentrations are similar and the Kas are similar, they're going to add together, right? Just like 2 strong acids. But they're not going to do that on a test because that's 2 problems. You don't have time for that, right? So, but if you got a Ka of -4 and a Ka of -8, why would you bother doing the one of -8? It's not going to contribute anything that's relevant when you have a Ka of -4, right? The -8 is going to be statistically and mathematically inconsequential. Okay? That's basically what this is saying. So you have to kind of like think to yourself and you have to kind of like say, okay, this is not really worth my running this calculation because when I add the 2 together, the decimal points are going to be too far away for them even to add together to make it worth my while, right? So let's take a look. So here's an example. Okay, so you're going to find the pH. of the mixture of 0.300 molar HF and 0.100 molar HClO. Now, it's really easy, ClO, okay. So it's really easy to say yes, but look at this is 3 times the concentration, right? So doesn't that make a difference? So then I'm gonna say, okay, but with every exponent, it's 10 times the amount, right? So if I go from -4 to -3, that's 10 times the amount. When we're talking about going from -8 to -4, that's 10 times 10 times 10 times 10. Is 3 going to make a difference? No, not at all. No difference at all. They are essentially the same concentration when you look at that. There's no difference. They are both 3 times 10 to the minus, they're both times 10 to the -1. Their concentrations relatively are the same with regard to the Kas. Okay? So let's take a look. So for HF, the Ka is equal to 6.8 times 10 to the -4. And for HClO, the Ka is equal to 2.9 times 10 to the -8. So, and then we have Kw still hanging in there, 1.0 times 10 to the -14th. Negligible. All right? So I'm going to take the HF and I'm going to start with it as if it is the stronger of the two, and I'm going to rely on that. So I'm going to start with my HF. I'm going to use my Ka. And then I'm also going to assume my 5%. When I solve for x, I get 1.4 times 10 to the -2. So that's definitely worth running a test. That's kind of close. So I run the test. And what I get is 4.7%. And technically, I am still good to go. So I'm going to do it, which means that that's my x, which means my concentration of H plus is equal to 1.4 times 10 to the -2, right? Now, if I were to run this again with x squared being equal to 10 to the -8, would that be worth adding on to this? No, it wouldn't, because it would be 10 to the -4. So sig fig wise, which is 2, it wouldn't make any difference at all. Do you see that? Because those 2 digits would be too far over to the right and would not even be calculated in. Does that make sense? So it's not even worth calculating them. So when I run my pH here, which is equal to -log 1.4 times 10 to the minus 2. I get 1.85, 2 digits for the two significant figures in my concentration. All right? So, to recount here, strong acids, because they are so strong, their hydrogens sort of overpower and they make any other calculation kind of statistically ridiculous, like 1.8 times 10 to the 4. There's really no point in running any other calculation. And so this was a really important example to run because this sets the tone for all of the other ones, all right? If it's two strong acids, then you add them together because it's 100% dissociation. So you're going to add them together and then dissociate them 100%, right? If it's two weak acids, on the test, I mean, if they're close enough together, obviously, if it's like two of them that have the same Ka, you kind of have to add the concentrations together, and that, you know, you're going to have to run them both because they're both going to contribute. But the bottom line is they're not going to make you do two problems on the test. That's just not realistic. So they're going to give you one that's larger and one that's small enough that you can ignore it. Because they want to know if you understand. They're asking you if you understand the statistical significance of the Kas. Okay? And one of them will be large enough. Natalie. So if you what? If you end up having to use both. You won't. But if you did, you would end up with two separate hydrogens, and they would be close enough that if you added them together, it would make a difference. So do you add them? Then you would add them together. So the other one would be like, I don't know, 2.6 times 10 to the 3. So you would, if you added them together, then the 2.6 would round off to a 3 essentially, right? And you would end up with plus 0.3. So it would make a difference, right? But they're not going to do that. Okay? All right. Bases, here we go. So bases obviously are the same as acids, only in the opposite direction, right? So a strong base has a 100% dissociation to OH minus. A weak base, and this is the one thing that's sort of interesting really to note, is that it looks kind of a little weird. So a weak base looks like this, which is sort of like, that's weird. Why would it look like that? Well, the reason is because it pulls off that hydrogen and it takes the OH minus. So what you end up with is something that looks like this, your Kb, and this is what's really important, looks like this with the OH minus and the BH plus, because remember, we're still dealing with Bronsted-Lowry's, right? And then on the other side is going to be whatever your base start was, right? So you're looking at your concentration of your hydroxide, and this is considered to be whatever your proton acceptor was. And of course, same as with the acids, the smaller the Kb, the weaker the base. Now, a good call on these tests is that if it has a nitrogen in it, it's probably a Bronsted-Lowry base. The reason is because the nitrogens have that lone pair. And so nitrogen acts as a base. Because that lone pair can accept a proton. So what happens is you get something that looks like this. So we have, let's say, ammonia. Right? We have ammonia. Plus, then we have the water, right? And so what happens is the ammonia takes on the proton, which now has a plus sign because it has that extra proton. And that's how it becomes NH4 plus. So we have NH3 plus water becomes NH4 plus, and then the hydrogen came off the water. So now we have the hydroxide hanging off there. And hydroxide is a super strong base. And ammonia is a moderately weak base. So water is a neutral acid, right? So this is like strong base, neutral conjugate acid, right? Weak base, pretty strong acid, conjugate acid, right? So this is the classic reaction with the base, like the hydrochloric acid reaction. This is the classic basic reaction because nitrogen acts as a base with that lone pair. All right, so here's some examples. Determine the concentration of hydroxide and pH. In 0.225 molar potassium hydroxide. So if you look on your list, all of the alkali metal bases are strong bases. So this is a 100% dissociation. So OH minus is equal to 0.225 molarity. So this is a strong base, which means that my H plus, so this is something to look at, my H plus, to find that, I'm going to take 1.0 times 10 to the minus 14, the KW, right? Because KW is always equal to H plus times OH minus. So minus 0.225. Is everybody okay with that? Do you want the formula? Want me to write down the formula?
Wait, is it minus or divided by?
Divided, right? And that gives me my H plus, which is 4.44 times 10 to the minus 14, which means my pH is negative log of that, which is 13.35. Questions? Now, I love doing this stuff. This is so, like, because it's just playing around with the formulas until I get what I need. So, all right. Letter B, Another example, 0.0015. So this is a very weak concentration of strontium hydroxide. So SR, it's an R, SR, strontium hydroxide. This is a strong base. Right on your list that I gave you, all right? So anything that's in the alkali metals or that's in the alkaline earth metals, they are all strong bases. But this one's a little bit different. Why? It has two hydroxides, right? So this one, when it dissociates, it's going to actually give off two hydroxides. So therefore, it's going to be this, and it's going to dissociate into SR plus 2OH minus. So now my concentration of OH minus is equal to 2 times 0.0015. This is not the same when we dissociate acids. So now my concentration of H plus, notice I'm switching writing styles of how I'm writing it because I want you to know that you can write it either way. That's why I'm switching, okay? Because you can write it as H3O plus or as H plus. You can write it however you want, but I want you to be able to read it in both directions, all right? Ten to the minus 14 divided by the concentration of the OH minus, 3.3 times 10 to the minus 12 molarity. So my pH is equal to 11.48. One more example, and then we're done. Okay, last example. So in this example, we're going to be using 0.100 molar NH3, which is not a strong base. It has a Kb of 1.76 times 10 to the minus 5, which should be listed on your list. So I'm going to need to do an ice table for this. Right, so we set it up, NH3. And remember, we're trying to find the hydroxide and the pH, okay? And then this is going to be, when this goes over, the NH3 is going to take on the H plus. That's what happens in bases. They get mixed with water, and they take on this is a proton acceptor. Anytime there's a nitrogen, it's a proton acceptor. So where does it get that proton from? Water, which leaves the hydroxide, okay? So this is going to be NH4 plus, and then plus hydroxide, right? So this is going to be 0.100 minus X. So I'm going to use my Kb. I'm going to test And as it turns out, it is good. So now my X represents my OH minus my H plus is going to be 7.6 times 10 to the minus 12th, and my pH is going to be 11 point. I'm going to go back up to my original. Notice that my KB has 3 digits. My concentration has 3 digits. My pH will be 11.124 with 3 digits after the decimal point. How are we doing? Everybody's okay? Nothing too new, just converting it over. Tomorrow we should be finishing this chapter. All right? Should be finishing it up. I think we're going to do solubilities. We're going to skip the next chapter and come back to it because solubility is just super similar to this. More of like the Ka and the Q and that kind of thing. So I think we're going to slide into that, and we'll do this chapter next, that chapter next, and then we'll test right before break on both of those chapters. And then when we come back, all we'll have is thermo and batteries. And so we should be able to finish them up and sort of pick up the pieces, I think. That's what I'm thinking. I'll have to take a look, but that's kind of what I'm thinking. Okay, I'm doing homework right now. That's what I'm thinking. 7. So it looks like 772 and 773 should do it. Keep that list with you. All right, you guys have a great night. I will see you tomorrow. Bye, Trent.